Hello, and this is going to be our 7A, which is going to talk about water and seawater. And today we're going to talk about just the water and the special properties of water. This is our first page, and we're going to talk about the Earth's surface being 71% water. Most of that by far is ocean water, and 29% land. This is the water cycle, and if you take a look at the amount of material that actually evaporates out of the ocean, plus what evaporates off the land, you get a total cubic kilometers, and that's kilometers. And then, of course, that condenses, precipitates out, most of it right back into the ocean. We put a good chunk of it onto the land, which allows us to have all the plants and animals that are on here. That runs off the surface. It actually goes in groundwater and runs off that direction. But basically, it's a cycle, and as long as the temperature stays the same, and as long as we get the same amount of sunlight, this is our water cycle. Of course, increased temperature is going to increase evaporation, which increases cloud cover, which bounces back solar radiation, which will somehow sort of even out the whole idea. But warming up the planet or cooling off the planet is not a good thing. We like it just the way it is. Okay, the atomic structure of a water molecule. It has a nucleus. Nucleus is the center. It's made out of protons, positively charged subatomic particles, and neutrons, neutrally charged subatomic particles. It's actually surrounded by an electron cloud, and lots of people like to draw it this way. And if you take a look at the number of protons in an atom, they are the same. So 3 protons in this atom, 3 electrons, except the electrons are actually in an electron cloud, which basically says they can be found anywhere in here at any time. They're spending more time in the center, of course, and then less time out here, but they're not in these nice little orbitals like you imagine planets going around the sun. We have ions. An atom is a neutrally charged atom. An ion is a positively or negatively charged atom. In the case of sodium, which sodium you actually see is located right here, these are what are called the noble gases, and all the things in here, they bond, and they're trying to bond to become like a noble gas. These are the only materials that do not bond, because what they've got their outer energy levels full. This is an energy level, and you can see it holds 2 electrons. So if you actually have 2 electrons normally, you're called helium. Hydrogen wants to become like a 2, and it'll do so very violently along with oxygen. And you see oxygen has to gain 2. We'll actually use 2 hydrogens to make that oxygen move over to here like neon, and molecules are neutrally charged. So this is a sodium ion. If you notice, its outer level has 1 electron. It very likable, like wants to give off this electron. It will do it very easily. So here's a sodium ion, here's a chlorine item. If you notice that chlorine is here, so this is a chloride. This is a sodium ion, and if you notice, it has this 1 electron, which will very easily give off to this one, which will cause chlorine to actually think it's got a full outside, make sodium think that it's got a full outside, except now we'll have a sodium plus ion and a chlorine minus ion, and what they do is they attract each other into this molecule called sodium chloride. And if you take a look, we've got the sodium ions surrounded by chlorine ions, and it makes this nice beautiful square pattern, which we'll talk about later. Okay, here's where's later. This is a sodium crystal, sodium chloride, and if you notice, it's got pink colors, because basically the difference is if it's bleached, it's this white color, which we like to use on the table, and if it's not bleached, this is like sea salt. I'm not sure we'd like to actually see salt the same color as pepper, but that's the way it works. So halite has this nice, beautiful, square, cubic, even if it's like in parts, cubic shape to it. If you've ever looked at sodium chloride from like salt, table salt, sprinkle it out on your hand, and if you look at it closely, it's got these. There are 2 videos here. I'm going to actually show you this one, and I'll zoom in to this one at different parts. Dead Sea, amazing natural phenomena.
Let's see what this guy's
And
up
of
to.
course,
Hey,
we got ads.
What up?
we gotta go skate.
Like this
Salt cube.
salt cube, it's amazing.
Now we are making our temple.
This is amazing. It's a perfect cubes. I will try to find new cubes.
Just sitting by the Dead Sea.
There is one. It's 100% salt.
All the rest of them are trying to be cubic as well.
Let's try to find another one.
Okay. This one is also the Dead Sea. This is traveling to the Dead Sea.
Right now, and I'm on my way to the Dead Sea. Got the tourists.
And you can see going around, it's really tough to see, but over these hills in a very low elevation is the Dead Sea. And they're still driving and driving. And they get to a resort. There's a pool.
Right on the beach.
And there's the Dead Sea.
Guys are getting the pool nice and clean for me.
And we go down toward the Dead Sea.
Or protect eyes and mouth from water and try to swim on your back.
There's the Dead Sea.
All along the shore are these, I think it's salt sands. Cool. About to take my first step into the Dead Sea. There it is. Oh, is that ever warm? Nice. Guys just relaxing on his back.
And if you notice how high they're floating higher than they would in a normal lake or even an ocean. And that's all because of the extra salt, making the water more dense.
Salt. People up there.
Yeah, using the salt as mud. And I think we do that here. Dead Sea mud. Not sure what it's supposed to do, but definitely covers the body.
My skin will be super soft. Yeah, I think floating in the Dead Sea definitely ranks as one of the coolest things I've ever
done. Okay. Beautiful location. And that red sky actually all had to do with the particles, the particulates that are actually in the water, or in the air, sorry. Water molecule. I call it a Mickey Mouse molecule, pretty obviously. Why? It is two H's and an O, two hydrogens, one oxygen, sitting at not 180 degrees, but 104.5 degrees. And they actually go with what's called covalent bonding. Covalent bonding is sharing of electrons. If you notice that hydrogen only has one, and what happens is oxygen says, I'll share one with you. If you share one with me, oxygen now thinks it has two. It's a helium. Hydrogen, sorry, thinks it's a helium. And oxygen is two off, and you can see that one right there and that one right there. So what it does is it says, I will be glad to share electrons with you, and I'll share electrons with you, and we'll both be a happy molecule, which is what molecules are trying to do. The bend in the geometry, it creates polarity. What happens is we have one more, well, actually I'll show it to you in a picture, but we have more electrons spending more of their time around this oxygen than they do around the hydrogens. So we have a little plus charge over here, and we have a negative charge. This makes what's called a dipolar molecule. Now the dipolar molecule does amazing things. Has a weak charge at the O end, has a weak positive charge at the hydrogen end. It forms hydrogen atoms or hydrogen bonds between these, so the plus end of one molecule actually attaches itself hydrogen bond Y to the negative part of this other, and what it does, it actually creates weak bonds between the water molecules and seemingly like the ions, and this explains some unusual properties of water. So here's the water molecule, the plus end, the minus end. The plus end attracts the negative end of one molecule, and we have these hydrogen bonds which break fairly easily. But what they do cause, and if you notice there is a water molecule and there's a water molecule, it attaches itself in all the directions to other water molecules. And inside the body of the water, the ocean or a lake or a river, they've got water totally surrounded them, but up here at the surface, they don't have any water above them. So what they do is they get strong strong bonding at the top, and this causes what's called surface tension, and that allows critters, if they can spread their weight out, notice that they're actually causing a concave layer in that water, and that is called surface tension. And here's another picture, and this is actually of a girl coming out of the pool, and the water still wants to hold on to water molecules, and before she actually breaks the surface, and this is what causes belly flops. If you've ever jumped in the water wrong, it hurts. It's basically the water saying, I don't want to break, and then you come out and it lets you come out fine. Okay, 2 unusual properties of water. First one is the high surface tension. Allows even lizards, if they can spread their weight out, to actually travel across the water. It's almost like the water has a skin. It's important to living organisms. It allows critters to move across. It actually allows capillary action. What happens is water molecules will pull up, and this is supposed to be an animation. Water molecules will grab onto the sides because they had adhesion as well as cohesion. Cohesion's when water's touching water. Adhesion's when it actually is, they have adhesion on there. Adhesion's when it actually touches something that's not water. So it actually grabs onto the tube, and if the tube has close enough sides, in other words a small enough opening, water will climb up, and that's what it does for plants. So it actually comes into the roots. High water to low water goes into the roots, and then it goes up these little tubes called the xylem, and goes up the tubes and actually goes out to the leaves, and then it pops out of the leaves, which pulls more water up and pulls more water up and pulls more water up, and it just continues to do that as long as we can keep water in the soil. It also is a universal solvent because of that positive negative dipolar charge of the water molecules. They'll actually pull things apart. Here's where they pull sodium chloride apart. They also do it with sugar. You guys know that it'll actually turn metal into rust, and actually make it so it can wash away in the next storm. But the big thing in this class is it makes the ocean salty. Water molecules, the plus end grabs onto the negative chlorine and rips it away from the sodium. The negative part on the positive sodium ion rips that away from the chlorine, and then we actually have chlorine and sodium chloride and sodium ions. Thermal properties of water. Water is a solid, a liquid, a gas on the Earth's surface. Under normal Earth temperatures, we can find water in all 3 phases. Solids, they're actually pretty well hydrogen bonded. Liquids, they're hydrogen bonds plus or minus, and gases, they're no hydrogen bonds. This has a set size, and a definite shape. This has a definite size, but will take any shape you want, and this has an indefinite size, indefinite shape. It'll take any size, any shape you want. Water also has a high freezing point compared to most materials. In other words, most things actually freeze at temperatures a lot lower than that. Water has a high boiling point. Most things boil before you get to that temperature. Water has a high heat capacity. There's only one material that has high heat capacity, and basically what this means is you heat it up and it shows a very small temperature change, or you cool it down and it takes a long time for it to cool. Water also has high latent heat, hidden heat, and I'll show you more about that here. Heat absorbed or released with changes in state or phases. So we're going from either a liquid to a solid or a liquid to a gas. Latent heat of, and if you notice, with melting and freezing happens at the same temperature and requires the same energy. The real energy zapper is when water goes from a gas. It's called evaporation, or it actually gives it up from a gas back to a liquid. So if this is 800, this is a lot more calories to get it to do that. So the heat released, changing solids into gas, actually releasing it, actually taking it into the water molecule, taking it away from the atmosphere, cooling the atmosphere, is 680. We have melting and freezing, the latent heat of melting and freezing. Temperature goes into breaking the hydrogen bonds, or to make the hydrogen bonds, and not a temperature change. Vaporization and evaporation, this one, and condensation, that one. Global thermostatic effects, moderates global temperature. This is called the global conveyor belt, and you can see water moving along the surface, especially in equatorial regions, very shallow currents, and we'll talk about these when we talk about surface currents. But what they do is they come up and then they move along the east coast of the United States for the Gulf Stream, and when they get up to this point they cool and they sink. So it actually brings warm water up to the poles. And then it takes the cold water away from the poles, brings it down underneath the tropics, down along Antarctica, and actually comes up in the Indian Ocean, cooling off the tropical water there, and also comes up over here around the Gulf of Alaska, which actually cools that water up there, so it can come back down and warm. And this is called the global conveyor belt, and they actually think that it can take thousands of years for water to go around this conveyor belt, because especially the ones that are down below are very slow, and we'll find those out later. Evaporation removes heat from the ocean, so when we actually evaporate water, you're adding heat to the ocean, and then that heat actually goes out to break the bonds and turn it into a gas, and what it does, it actually cools the ocean. That also tends to heat up the atmosphere, so we can actually heat up the atmosphere by making clouds. It redistributes the heat globally. Here's the Earth's energy budget. So again, 100% comes in. You got to actually have 100% coming back out. Some of it never even reaches the Earth, but of the part that reaches the Earth, which is a little over 51%, we actually find it all leaves. And this is the budget. What we don't want is don't want a lesser amount coming in. We also don't want this amount coming in and we have a greater amount bouncing off clouds, or we actually have a greater amount actually trapped by the atmosphere, so it actually heats up the planet. Differences between day and night, if you take a look at, these are degrees Kelvin, and there are no degrees Kelvin, these are just Kelvin. So this is -9, and where do you see this is actually basically colder temperatures. You can see them mostly up there, and they would also be down here. Where do you see the biggest degree change? These 29 degrees, they happen right around the tropics, and especially in the real tropics. So it actually gets really hot there, and the temperature drops quite a bit, especially in the deserts. Water density. Water is maximum density at 4 degrees Celsius. If you take a look at the temperature scale, winter it's pretty much cold all the way down. This would be like a pond or a lake. In the spring, the surface actually starts to warm. In the summer, it's the warmest, but if you ever go back down, this is actually 10 meters, even down a little bit especially a lake that does not get churned up like this one does, you actually find what's called a thermocline. It's a very quick drop of temperature along a very horizontal line. And then fall, of course, you get more storms. The water gets kicked up, and again, this is not the ocean. The ocean's never going to do this. The ocean will always be 4 degrees Celsius at the bottom, and it may actually warm up at the surface, but we're not talking about 90 meters of water. We're talking about 11,000 meters at the Marianas Trench. Ice is less dense than liquid water, and that's why it floats. And there's always the 10%, 90%. Why boats don't want to come up to icebergs is because there's 90% of that ice underwater, and it tends to be as hard as rock. Atomic structure of ice. Again, if you have vapor, there's no hydrogen bonding. If you have liquids, you have some hydrogen bonding. And if you have solids, it's completely hydrogen bonded. And if you take a look, it actually spreads out, which tends to make ice take a larger volume. It has the same density. Larger volume makes it less dense, which is why ice floats. Increased salinity decreases temperature, maximum density, and what this basically means is we can add salt to water, and we can actually make it melt the water for the ice that's there. Here's a picture of actually ice, and if you notice, ice is very spread out, and if you get to 0 degrees Celsius or 32 degrees Fahrenheit, what you find is an incredibly very quick increase in density. So we actually have less dense there. It starts to increase, and then as you cool it down from 0 to 4 degrees, it actually goes from its least dense all the way up to its most dense. So it actually is less dense, and it floats there. And this isn't showing floating, this is talking density, but the lower this is, the less dense it is, and the higher it floats. And then this is the most dense, which means it's at the bottom. And then this picture is actually showing you temperature again down at the bottom, and it shows salinity here, and this is the freezing point, and at 0 degrees 32 in fresh water it turns solid. But as we add salinity to the water, as we add salt to the water or sugar to the water or some material in the water, what we find is the freezing point actually drops down. So you can get up to a salinity of right around the ocean and find that it can actually decrease the freezing amount. In other words, water would actually freeze not at 0, it would have to cool down to 1 degree Celsius, or that's probably about 30 degrees Fahrenheit before it freezes. And as you increase the salinity, the water will actually stay liquid even longer. This is the water density. This is actually the liquid part of the water. This is where water actually increases, and it actually decreases with decreasing temperature. But this is the line we're trying to get, especially in a few months when we actually get ice forming on the roads. This is why they salt the roads. And then the last slide, solids, totally hydrogen bonded and expanded and less dense. Liquid, partially hydrogen bonded, and why you can jump into it, you can break these bonds, although you want to break very small numbers of them, allowing you to go in rather than doing a belly flop and trying to break out a whole bunch of them. And gases, no hydrogen bonds. A very definite size and shape. This has a definite size with an indefinite shape, and this has an indefinite size and an indefinite shape. And that is where we lead off. Thank you much. See you in B.